It is a common phenomenon that a hot body exchanges heat with its surroundings and cools. The heat lost by the body to its surroundings per unit time is called the rate of cooling of the body and depends on several factors. Let's conduct an experiment to study the factors that influence the rate of cooling of a body. Let's take some water at room temperature in a calorimeter and place in it a thermometer. If the temperature of the water is T1 degrees Celsius, then the temperature of the surroundings is also T1 degrees Celsius. Now, let us first heat the water in the calorimeter to raise the temperature to say T2 degrees Celsius. And then stop heating and allow the water in the calorimeter to cool. Start a stop clock and note the temperature T2 of the water at regular intervals, say after every minute. The difference in temperature between the water and its surroundings is expressed as delta T, which is equal to T2 minus T1. Delta T can be computed for each value of T2. When a graph is plotted by taking delta T along the y-axis and time t along the x-axis, we get a curve. The graph indicates that the cooling of water depends on the temperature difference between the water and its surroundings. The greater the temperature difference, the greater the fall in the temperature of the hot water. With the passage of time, the temperature difference between the hot water and its surroundings decreases, and hence the change in the temperature of the water also decreases. Newton made a systematic study of the cooling of different bodies and proposed a law known as Newton's law of cooling that holds good for small differences in temperature between a hot body and its surroundings. Newton's law of cooling states that the rate of heat lost by a body is directly proportional to the difference in temperature between the body and its surroundings. If a body is at a temperature T2 degrees Celsius and its surroundings are a temperature of T1 degrees Celsius, where T2 is greater than T1, then the rate of loss of heat is expressed as minus dQ by dt is proportional to T2 minus T1, or minus dQ by dt is equal to K into T2 minus T1. Let this be equation 1, where K is the proportionality constant, which depends on the area and nature of the body. Let the mass of the body be m, whose specific heat capacity is S, at an initial temperature T2, with its surroundings at a temperature T1. If the temperature of the body is changed by delta T2, because of a small loss of heat delta Q, in a small interval of time delta T, then delta Q can be expressed as a product of M, S and delta T2. Then, the rate of heat loss is equal to delta Q by delta T equals to MS delta T2 by delta T. Let this be equation 2. But according to Newton's law of cooling, we have minus delta Q by delta T is equal to K into T2 minus T1. Let this be equation 3. Combining equations 2 and 3, we get minus ms into delta T2 by delta T is equal to K into T2 minus T1. Or delta T2 by T2 minus T1 is equal to minus K by ms into delta T. Let this be equation 4. Taking limits on both sides, we get dt2 by T2 minus T1 is equal to minus K by ms into dt. On integrating this expression on both sides and simplifying, we get log to the base e T2 minus T1 is equal to minus K by ms into T plus C. Let this be equation 5. This can also be written as T2 minus T1 is equal to e to the power minus K by ms into T plus C, which is equal to e raised to the power C into e raised to the power minus K by ms into T. Let this be equation 6. If we define K equal to K by ms and C equal to e raised to the power C, then equation 6 becomes T2 minus T1 is equal to C into e to the power minus kt, or T2 is equal to T1 plus C into e to the power minus kt. Let this be equation 7. This equation can be used to calculate the time taken for a body to cool through a particular range of temperature. The law is applicable to small temperature differences. Even when the transfer of heat is due to a combined effect of conduction, convection, and radiation, the rate of cooling is proportional to the difference in temperature. For example, if a beaker of hot water placed in surroundings whose temperature is 25 degrees Celsius takes 5 minutes to cool from 75 degrees Celsius to 50 degrees Celsius, how much more time does it take to cool to 30 degrees Celsius? Using Newton's law of cooling, minus delta T2 by delta T is equal to K into T2 minus T1. Therefore, minus delta T2 by T2 minus T1 is equal to K into delta T. Let this be equation 1. This can be written as a change in the temperature by temperature of the body minus temperature of the surroundings is equal to K into time. It is given that the initial temperature of the body is 75 degrees Celsius and its temperature after 5 minutes is 50 degrees Celsius. Since the temperature of the hot body is not constant, the average of the initial and final temperatures has to be calculated to arrive at the value of T2. When the body is cooled from 75 degrees Celsius to 50 degrees Celsius in 5 minutes, the average temperature of the body is the average of 75 degrees Celsius and 50 degrees Celsius, which is equal to 62.5 degrees Celsius. Delta T2 is equal to minus 25 degrees Celsius. Minus delta T2 is equal to 25 degrees Celsius. Delta T is equal to 5 minutes. Substituting these values in equation 1, we get 25 by 62.5 minus 25 is equal to K into 5. further simplifying, we get K is equal to 5 by 37.5. Now, the values to calculate the time for the water to cool from 50 degrees Celsius to 30 degrees Celsius are the average of 50 degrees Celsius and 30 degrees Celsius is 40 degrees Celsius, and hence T2 is equal to 40 degrees Celsius. T1 is equal to 25 degrees Celsius. Delta T2 is equal to minus 20 degrees Celsius. Minus delta T2 is equal to 20 degrees Celsius. We need to find the value of T. (20 by 40 minus 25 is equal to K into T. On further simplifying, we get T is equal to 4 by 3K. We know that K is equal to 5 by 37.5. Substituting the value of K, and simplifying, we get the value of T equal to 10 minutes. Therefore, it takes 10 minutes for the temperature of the water to fall from 50 degrees Celsius to 30 degrees Celsius. Newton's law of cooling can be verified by conducting the following experiment. A double-walled vessel is filled with water between the walls, and the mouth of the vessel is closed with a cork through which a thermometer is inserted. Let the temperature reading be T1 degrees Celsius. A copper calorimeter with hot water is placed inside the vessel. Close the mouth of the calorimeter with a 2-holed cork. With a stirrer passing through one hole and a thermometer through the other, let the reading in this thermometer be T2 degrees Celsius. The temperature of the hot water in the calorimeter is noted after equal intervals of time. When a graph is plotted with log to the base e, T2 minus T1 along the y-axis and time t along the x-axis, based on the experimental results, we get a straight line with a negative slope.